Welcome to Lecture Online, and here's another example, example number 4 on applications of Newton's second law. Here we have an interesting wedge-shaped object with two masses on it connected with a single string. This one is 6 kilograms, that one is 15 kilograms. Notice that the slopes are different. And what would be the acceleration of this system? And notice again, it's a system. These are two masses connected together, so you can look at it as a single system. We have to draw all the forces acting on the system. So we have the weight pulling straight down on this one right here. So this is m1g. Of course, we have the perpendicular component of that, which would be m1g cosine of theta 1, because it's this angle right here. And then we have the parallel component, which is m1g times the sine of theta. And now, of course, that would be theta 1. Over here, we can do the same thing with this mass. Here we have the weight pulling down, which is m2g. Of course, we have the perpendicular component this way, which would be m2g cosine of theta 2. And we have this component right here, which is the m2g times the sine of theta 2. So the parallel component is acting along the incline. The perpendicular component is perpendicular to the incline. Of course, we have the normal forces. Newton's third law indicates that there would be a reactionary force here, which we call N1, which is opposite in direction to m1g cosine theta 1, equal in magnitude. And then, of course, here we have N2. Again, it's equal in magnitude to m2g cosine theta and opposite in direction, so that these cancel each other out, these cancel each other out. Of course, this one is gone because I divided that into the components. That one is gone as well. So we only have two forces left, which is this force, m1g sine theta, pulling the whole system in this direction, and here we have m2g sine theta 2, pulling the whole system in this direction. This being a heavier object on a steeper incline, I would think that this is a bigger force than this, and therefore I would assume that the whole system would be accelerating in this direction. So I'm going to call acceleration in this direction to be the positive direction. Okay, now I'm using Newton's second law that says F net is equal to mass total times acceleration. If I then rearrange that equation to solve for A is equal to F net divided by m total. And of course, the net force will be all the forces aiding the acceleration minus all the forces opposing the acceleration. This one is aiding, this one is opposing, so this would become m2g sine of theta 2 minus m1g sine of theta 1. That would be the net force acting on the system divided by the total mass, which is m1 plus m2. That would give me the acceleration of the system. Let's plug in the numbers. I'll leave out the units to make it a little cleaner. m2 was 15, g is 9.8, and we have the sine of 50 degrees minus m1, which is 6, g is 9.8, times the sine of 30 degrees, which of course is 1/2, all divided by the sum. m1 is 6, and m2 is 15 kilograms. So of course, then the units of this would be meters per second squared. So with a calculator, what do we get? 15 times 9.8 times the sine of 50 minus 6 times 9.8 times 0.5 equals, and take that divided by 21, the acceleration would be 3.96 meters per second squared. All right, so now we found the acceleration. Now we need to find the tension in these strings, and of course, we should already know that T1 equals T2, assuming that there's no friction in the pulley, and we can assume no mass in the pulley, so we don't have to worry about its moment of inertia. All right, so what we can do now is we can simply say that the tension 2, I can do either way, but I'll start with tension 2. Tension 2 is equal to the weight component along the incline, which is m2g sine theta, so it needs to have at least enough mass to hold up against this weight. So the m2g sine of theta 2 plus or minus, and we'll decide if it's plus or minus, the force required to accelerate this. So the force required to accelerate m2 with the acceleration that we found, the 3.96 meters per second squared. Now, is it plus or is it minus? It would be plus if the mass was being accelerated upward. It'll be minus if the acceleration is allowed to go downward with the force of gravity. So in this case, we can say that it's going to be minus. Now we plug in the numbers. M2 is 15, G is 9.8, sine of 50 degrees, minus M2, which is 15, times acceleration of 3.96. And again, units would be, of course, newtons in this case. 15 times 9.8 times the sine of 50 minus 15 times 3.96 equals, that's better. So the tension in the string would be 53.2 newtons. And of course, that would also be the same for tension 1, since it's a single string with a massless, frictionless pulley in between. And that's how you do a problem like that.